Section 20.4 Electronic Spectra of Complexes. Subsection E Tanabe-Sugano Diagrams. You're looking at the Tanabe-Sugano diagram for the D2 electron configuration. So you have two electrons in the 5d orbitals. There are 45 microstates that can be grouped into 5 atomic terms: 3f, 1d, 3p, 1g, 1s. This 3f term is the ground term with the lowest energy. And then if you look at this 3p, it has higher energy than 3f. How much higher? 15b, higher than 3f. So now you look at this energy in terms of the numbers of b's. So this is 15. For the 3D transition metal elements, the Raka parameter C is equal to 4b. And then if you look at the Raka expression of the energies of all those atomic terms, I think 1d is about 13b above 3f. 3p is 15b above 3f. So that's why you can see this is around 15, this is around 13. You can use the Raka parameters and Raka energy expression to get this 1g and 1s energies relative to this 3f. But if you are using this Tanabe-Sugano diagram to predict the UV Vis spectrum of the D2 transition metal complex, I would suggest you to ignore the 1D, 1G, and 1S terms and their corresponding terms in the octahedral environment. The reason is, from a triplet spin state to a singlet spin state is strictly forbidden in the electronic transitions. So anyway, you're not going to see peaks in the UV Vis spectrum that corresponds to this 3f to 1d, 3f to 1g, or 3f to 1s. You're going to see the transition from 3f to 3p in the UV Vis spectrum of a free transition metal ion. Now if you put this ion in an octahedral environment, we'll have to take delta O into account. Delta O is the crystal field splitting. And when delta O is large, we'll see this 3f splits into 3T1, 3T2, and 3A2. When delta O is large, the gap between this 3T1 and 3T2 gets large. Between 3T2 and 3A2 becomes large as well. Now the energy difference between this and this is simply 1 delta O. The energy difference between this 3A2 and 3T1 is 2 delta O. Alright? The reason is very simple. Over here, we have both electrons in the T2G orbitals. Over here, one electron in T2G, one electron in the EG orbitals. Over here, both electrons are in the EG orbitals. And in an octahedral environment, the EG orbitals have higher energy than the 3 T2G orbitals by delta O. Also, you can just define the barycenter as the average energy of this 5d orbitals. And then the EG orbital lies 0.6 delta O above the barycenter. The T2G orbitals lie 0.4 delta O below the barycenter. So this is why this 3f splits in an octahedral environment. And the larger the delta O, the larger the gap between these three terms. Now let's look at 3p. Again, the 3F to 3P transition is being allowed. So it's possible to observe the electronic transition from 3F to 3P for a free transition metal ion. Now, if we put this transition metal center in octahedral environments, again, this 3F splits. So now we're going to see, 3T1 to 3T2 transition, 3T1 to 3A2 transition, and also 3T1 to this 3T1 transition. So this 3T1 originates from this 3P. All right. And the difference between 3P and 3F is 15B. So supposedly over here, the difference is also 15B. However, over here, the value of B is smaller than the value of B here. The reason is, when you have a free transition metal ion, you have a larger B. Okay? When you have multiple ligands surrounding this transition metal center, the d electrons are slightly dispersed into the ligands. And that means the repulsion between these two d electrons is slightly smaller. So that's why you have a smaller B here. Again, this is also 15B. This is 15B, but over here, this 15B is smaller than here. And this 15B originate from this 15B. And why 15B? Again, it's the Raka's equations for the relative energies of these 5 atomic terms. Now, why is this useful? Again, we can just use this to make predictions. If we know delta O is 20 times B, this is pretty common. Because delta O is 20,000 wave numbers, plus minus 10,000. This parameter B is roughly 1,000 wave numbers, plus minus 300 or 400. So in a typical case, if we have delta O is 20 times B, and then we just look at this horizontal axis, find the ratio. Delta O is 20 times B, it's right here. And then we can look at the transition energy from 3T1 to 3T2. So this dashed line is 3T2. And also from 3T1 to this 3T1. So this is from 3F. This is from 3P. And also we can look at the transition energy from 3T1 to 3A2. All right, so we just look at this. Well, of course, because this is just the D2 electron configuration. So we know that this transition is supposed to be delta O. So it's going to be just 20B. So over here, this is roughly 20B. Okay? And then 3P is 15B above 3F. So this line is roughly 15B above this line. So over here, this is 15B above this 20B. That's 35B. So if you draw a vertical line here, it's 20B, and then 35B, and then 40B. All right, so if delta O is equal to 20B, and then we can predict the transition energies are 20B, 35B, and 40B. What if delta O is equal to 15B? Well, the transitions is going to be 15B, and then 15B plus 15B, that's 30B. And then 2 times delta O, which is also 30B. So you have this cross point here. Both are roughly 30B. So 15B, 30B, 30B. All right, that's how we use Tanabe-Sugano diagram to make predictions of the UV vis spectra of the D2 transition metal complex. Okay, using this diagram. Over here, you can see I'm just giving some typical values for delta O, 20K, B, 1K, and then if delta O is equal to 20B, in this case, 20 over 1,000, the ratio is 20. And then we can predict that the transition is from 0B to 20B to 35B and to 40B. All right? There's three energies. And we learned that B over here, well, it's given to you. Let's say B is 1000 wave numbers. And then in the UV Vis spectrum of the D2 transition metal complex, the three peaks will have this wave numbers: 20,000 wave numbers, 35,000 wave numbers, and 40,000 wave numbers. And then you can calculate lambda in nanometers. So in this case, we have 20,000 wave numbers. The lambda value is 500 nanometers. This is within the visible range. This two. I think this one is roughly 300 nanometers. This one is roughly 250 nanometers. So these two are in the ultraviolet UV range. All right, but again, I mean, I made these predictions based on these given values of delta O and B. And of course, B can be from actually 600 to 1300 for the 3D transition metal elements. Delta O is typically between 10,000 to 30,000 wave numbers for 3D transition metal elements. All right, big range over there. So this is just one specific numerical example. We can also look at some other electron configurations. If we look at this specific example, this is D3 transition metal complex. The electron configuration of the chromium atom is 4s2, 3d4. But in a transition metal complex, we need to give the 4s electrons to the 3d orbitals. So you have actually 6 d electrons. And then we take this 3 plus charges into account. There are actually only 3 d electrons. So this is a D3 complex. This ammonia ligand is in the middle of the spectrochemical series because it's not a pi electron acceptor. It's not a pi donor either. So it's in the middle. Well, that's why the delta O of ammonia should be close to 20,000 wave numbers. Now, if you look at the UV Vis spectrum of this transition metal complex, you'll see two significant peaks at around 21,000 and another at around 28,000. How do we interpret these two wave numbers? Well, we can also use the Tanabe-Sugano diagram for the D3 complex. So first, we can take a ratio between these two wave numbers. So this 28,500 over 21,500 is 1.32. Now I'm going to show you the Tanabe-Sugano diagram for the D3 configuration. So that means we need to look at those curves and find two data points. Okay, blue data points. Because from blue to red is spin forbidden. So we'll have to focus on this blue line and this one and this one and this one. Those are spin allowed, and we can observe significant electronic transition between 1, 2, 3, 4. These 4 blue terms. All right, we calculate the ratio between the first two wave numbers. It's 1.32. And then we look at this Tanabe-Sugano diagram. When delta O is roughly 33B, so around here, we can see there's the first wave number, and then here you have the second wave number. The first wave number is 21,500. The second one is 28,500. So at this position, when delta O is 33B, we look at this arrow, longer one, and we look at this shorter arrow. We use the length of the longer arrow divided by the length of the shorter arrow, you get 1.32. So there's a match, 1.32. Alright, so over here, I think this is roughly 42B. And this is roughly 32B. Okay, roughly, okay? And 42 over 32 is roughly 1.32. And then we get the correct ratio. So again, if you have the UV Vis spectrum, you look at these two peaks, the first two spin allowed transitions, get their wave numbers, take the ratio, you get 1.32, and then you look at this Tanabe-Sugano diagram, okay? And this is the ground term. You need to look at the first excited term, the second excited term, and then you take the ratio between this transition and this transition and try to find the same ratio, 1.32. You find it here, and then you can determine that the first transition has a transition energy of 32B, the second one 42B. Alright? And then we can plug in these two equations. 32B is roughly this, 43B is roughly that. There are two equations to solve for B. They are going to be slightly different. It's okay. Again, Tanabe-Sugano diagram is just an approximation for us to analyze the UV Vis spectra of transition metal complexes more conveniently, not accurately. So it's really convenient, but it's not very accurate. So if you solve these two equations, you might get two different values for B. If that's the case, I would say, well, just take the average. My result is this. B is roughly 670 wave numbers, and this is quite reasonable. Between 600 to 1200 or 1300 is quite reasonable. And B is smaller when you have multiple ligands surrounding the transition metal, because those ligands can help disperse the d electrons. That will reduce the electron repulsion between those d electrons, and then you have a smaller B. And over here we know delta O is equal to 33B, because when delta O is 33B, we find the ratio is 1.32. This ratio matches with the ratio between the two peaks in the UV Vis spectrum of this compound, okay, 1.32. And then we can compute delta O. Delta O is 33 times B. It's just 22,000 wave numbers. 22,000 wave numbers. So I think this makes sense for this ammonia ligand, roughly 22,000. But again, I want to emphasize that those numbers are just rough estimate. Those numbers are rough estimate. Another way to solve the same problem is this. Okay, we have these two wave numbers, 28,500, 21,500. And we know the difference between 3F and 3P is 15B. It's this prediction or this equation was proposed by Raka, okay, and ABC are Raka parameters. So the difference is around 7,000 wave numbers, and that's approximately 15B. So you use 7,000 divided by 15B. Again, you can estimate the value of B. So that's, I think, roughly 500 wave numbers. Well, it's smaller than this. It's smaller than this number. But again, those are all rough estimates. Okay, semi-quantitative analysis. Okay. Now, we'll look at another example. We're going to use the same Tanabe-Sugano diagram for the D3 transition metal complex to predict the energy of the first two spin allowed quartet bands in the spectrum of this? Well, this is hexa aqua chromium 3. Here, delta O is given to us, B is given to us. So delta O is 17,600 wave numbers, B is 700 wave numbers. Well, in this case, we calculate the ratio between delta O and B. So this divided by this, it's roughly 25. Why do we need to know this ratio, delta over B? Look at this horizontal axis. Delta over B is equal to 25. So we can just look at here. And then we move up. Okay, we move up. Over here, this is going to be your first transition. Okay, from 4A2 to 4T2. That's the first spin allowed transition. This one is, I think, roughly 25B. Okay, this is 20B, it's 30B. And over here, it's roughly 25B. What about the second transition? The second transition is from here, 4A2 to 4T1, spin allowed. So over here, roughly 33. Okay, you need to draw a vertical line from 25B all the way up, and then check the relative energy in terms of B. I think it's 33B, 34B. Okay, anyway, I got this 25B here and 33B here, and we just do a multiplication. 25B is this much, 33B is this much, and this is my prediction of the wave numbers of the first two peaks in the UV Vis spectrum of hexa aqua chromium 3.